All right, guys, it's 7, so we're gonna go ahead and start. Today we're gonna build on what we talked about last class and the class before that, and we're going to talk about some more constructions. And we're also gonna introduce the circumcircle and the incircle. That's gonna be a little bit of lecture, so you might want to listen, but the rest of it are constructions and it's very interesting. So the first thing we're gonna do is we're gonna do a construction of an angle. Hi, Joyce. Joyce, today we're doing something very similar to last class and the class before that. We're gonna talk about constructions, but we're also gonna talk about circumcircles and incircles. So we're gonna start off with bisecting an angle. So say that I have an angle like this. By the way, you guys can see the screen, right?
Yes.
Okay. So let me just hide these points for the sake of clarity. All right, so to bisect this angle, we're gonna start by drawing a circle like this. And we're gonna draw these points. Connecting them gives this triangle. And since this is a circle, we know the radii are equal. So AE is equal to AD, which means they're the same in terms of length. So recall that last class we learned about how to construct a perpendicular bisector, which is a line through the midpoint of a given line segment that is also perpendicular to that line segment. Since we know this is an isosceles triangle, we know that a perpendicular bisector of ED will also be the angle bisector of angle EAD. We're gonna talk about this more in depth after this construction because I want to start with this just to give you a bit of idea of what we're talking about. But keep in mind that we're gonna go back to the concept of angle bisectors later. So to bisect this angle, we're gonna construct the perpendicular bisector of line ED. Joyce, do you remember how we do that?
No.
All right, that's fine. Lloyd, you remember? All right, that's fine. That's fine. So remember what we do is we draw two circles with a radius of EA or DA. And if you connect A and the other intersection point, you get the perpendicular bisector. And just to prove that, I am going to measure this angle. That's interesting. It doesn't let me point that point there. Just to prove that, I am going to measure this angle. And indeed, it is 90 degrees. So that's how you construct a bisector of a given angle. So does that make sense to everyone? Do you guys have any questions? I know you guys are kind of fuzzy with the perpendicular bisector still. So I could go over that again if you guys want. What do you guys think? Questions? Joyce, is this clear to you?
Yes.
Okay, that's great. Then in this case, we're gonna talk about circumcircles and incircles. So we're gonna start with circumcircles. Let me delete all of this real quick. All right, so first of all, since we're all kind of forgetful, I'm gonna talk about the definition of the perpendicular bisector again. So remember, the perpendicular bisector of line segment AD
Some shit 啊，他在招了。
Hi, David.
这些人都不逗脸，真伪。
David, you might want to, okay. Yeah, so recall that the perpendicular of line segment AD is the line through the midpoint of AD, which I'm going to call here as E, such that the line is perpendicular to AD. And from last class, we learned that you construct it by, I'm actually not going to even use this point, you construct it by drawing two circles like this. And you would end up with the perpendicular bisector. And since it is the perpendicular bisector, we know G is the midpoint of AD. And this line down the middle is perpendicular to AD. And now I want to prove something regarding perpendicular bisectors. So what I want to prove in this little exercise right here is that we're going to prove that if this point A right here is equidistant from points D and E, then A is on the perpendicular bisector of these 2 points. Is the objective clear to everyone?
Yes.
Okay, great. So what we're gonna do is we're gonna draw a line down the middle. And since we know that AD is equal to AE, actually, is there a way I could let me annotate? All right, this is great. This says AE is equal to AD. And as I just mentioned, F is a midpoint. We drew the point to the mid, we drew A to the midpoint of line ED. So therefore, these 2 segments are also equal. By the way, these little hash marks imply that these side lengths are equal. So AD is AE and DF is equal to FE. And so these 2 triangles, ADF and AFE, are congruent to each other via SSS congruence, which is something we went over a couple weeks ago, if you guys remember. And what SSS is saying that is if 3 sides of 2 triangles are exactly equal to each other, which you can see in this case, AD is equal to AE, AF is equal to AF, and DF is equal to FE. Since all 3 pairs of sides are equal, the triangles are congruent to each other, which kind of makes sense, right? Because if you have a triangle and all 3 of its sides is completely equal to another triangle, then it would make sense that the 2 triangles are congruent, right? So since these 2 triangles are completely equal, we know that these 2 angles, this one and this one, are equal, right? Like that makes sense, right, everyone? And since DE is a straight line, we know that these 2 angles add up to 180 degrees. So someone tell me what that measure of AFE is. Joyce, do you want to solve this problem? So we know this angle, which I'm gonna call X for the sake, oh, that's a very, all right, I'll just call it A then. All right, so these 2 angles, which we're gonna call their measures A, they add up to 180 because a straight line is 180 degrees, right? Wait, Joyce and Lloyd, do you guys understand like why a straight line is 180 degrees?
Not really.
All right. So I guess we have to backtrack a little. Okay, so it's actually a really simple concept. So How do I? So let's say we have a circle. And I'm gonna draw a line through here. So what we have to start with is the angles in a point, like surrounding a point, like the angles in this entire circle is 360 degrees. Does that make sense, Joyce? Like the amount of degrees surrounding point G is 360 degrees. As in like 360 degrees is the maximum number of degrees any angle can have, and that's a complete circle. Does that make sense?
Yes.
Great. And if we draw a diameter, that splits the circle in half, which means, and if you split an angle that's circle in half, you would get a straight line, like a semicircle, right? So like I can't really erase this, but I'll draw it. It's like if you have half a circle, you would have a semicircle like this. The center of angle is this point right here. So since a whole circle is 360 degrees, half a circle is 180. Does that make sense?
Yes.
Great. So we have now proved that there is 180 degrees in a straight line. So that means if these two angles, which I'm going to call X, are completely equal and they add up to a straight line, aka 180 degrees, what is the value of X? Joyce, Lloyd, do you guys want to solve this equation? It's like thinking if you have two numbers that add up to 180, what is that number? $90. Yep, that is correct, Lloyd. Therefore, we know that these two angles are 90 degrees, which means it is indeed a perpendicular bisector. And recall that what we were trying to prove is that if this point A right here is equidistant from D and E, right? Like you see these little hash marks on line segment AD and AE. We're saying that if they're equal, then A has to be on the perpendicular bisector of line ED. Does that make sense to everyone? Lloyd, Joyce, does that
Yes.
concept make sense? Okay, great. Okay, because we're actually gonna use this concept to talk about how the perpendicular bisectors of a triangle are congruent. So let me erase this real quick. All right. So today's concepts kind of like build on each other. So if you don't understand anything, make sure to tell me because it's gonna affect like your understanding of the concepts later. Okay, so say that we have a triangle ADE, and for some reason it keeps on giving me these, keeps on ignoring BC. Let me let me restart this page real quick. Show axes, no grid. All right, that should be good. Say that I have a triangle ABC. It's much better. What we want to prove is that the three perpendicular bisectors of the triangle are concurrent. Concurrent means that the three line segments meet at a single point. And let me write that down so in case you don't. Concurrent means three lines meet at a single point. All right, so you have that note there. That's kind of nice. All right, so again, we're trying to prove that if I draw lines like this, okay, this is gonna be a rough idea of what we're trying to prove. because it's not a geometric construction, therefore it's not accurate. But what we're trying to prove is that if I draw these perpendicular bisectors of a triangle, they're going to meet at a single point. Does that make sense to everyone? Like, this is what we're trying to prove. We're trying to prove that the three perpendicular bisectors of the triangle meet at a single point. All right, I'm assuming there's no questions. All right, then, so let's head on with the proof. So how you tackle a problem like this is you would start by considering two of the lines, because we know that any two lines that aren't parallel has to intersect, right? Like if you have two lines that aren't parallel, they intersect at some point. And we're going to try to prove that this third line intersects the two other lines at the same point that they intersect them. So for example, we're going to start with we're going to start with the perpendicular bisector through BC. Hey, Kimmy, we're talking about constructions right now, and we're talking about circumcircles. If you have any questions, feel free to ask me. But
where's the other teacher, Eric?
Oh, he's taking a break today. But
anyway, this isn't exactly the center.
Oh yeah, well, you see, the circumcenter actually is different from something called the center of mass. Like the center of mass, like the center of a triangle.
Oh, it means like the heaviest spot.
Right, it would be like, yeah, but the circumcenter can be anywhere. And yep, and the circumcenter, because you missed it, it's like the circumcenter is the intersection of the perpendicular bisectors of a triangle. For example, the bisector of AC, the bisector of line BC, the bisector of line AB. Right now, we're trying to prove that they intersect at a single point. And as I was saying, we're going to start with these two bisectors. And we know that the point they intersect at, okay, that's not very exact, point H. You guys see this point right here, point H? So this is the intersection of two of the perpendicular bisectors. And using the result we just proved earlier, since H is on the perpendicular bisector of line segment BC, we know that it's equidistant from B and C. Does that make sense to everyone? Like, these two line segments are equal to each other. And since H is on the perpendicular bisector of AC, the perpendicular bisector of line segment AC, we know it's equidistant from A and C, meaning HA is equal to HC. So, what have we just discovered? We discovered that these three line segments are completely equal to each other. Right?
What do you mean?
Like they're the same length to each other?
How do we know?
Well, Kimmy, we actually just proved this result. I'm gonna show it to you real quick. That if a point here, K, is equidistant from I and J, then it is on perpendicular bisector of line segment IJ. Does that make sense?
Oh, I get it now. I get it now.
All right, that's good. That's good. But anyways, we're using that result right now. So we're saying that since H is on the perpendicular bisector of BC, we know it's equidistant from B and C, right? That makes sense?
Yeah.
Good. And using the similar logic, since H is on the perpendicular bisector of line segment AC, it's equidistant from A and C, right?
Yeah.
Good. And so we know that these three line segments are equal to each other, meaning HA is equal to HB. Someone tell me what this means for H.
Does that mean H is the center of mass?
Well, not quite, but what I want to emphasize on is line AH and line BH. Like we know that H is equidistant from A and B. What does that mean,
That
Joyce?
means C is the same thing.
Well, not quite, but you're kind of close. Think this. Think something about perpendicular bisectors. We know H is equidistant from A and B. What does that mean for H? We can deduce that H is on some sort of line that relates to AB. But what is it? Guys, remember the result we just proved? If a line is here, 2 points on the end, and a point is equidistant from these two, so the distance these here are the same, then the point here is on the perpendicular bisector. Right? Guys, remember this? We proved this a couple of minutes ago. So if we use this on H, B, and A, what does that mean? We know H, A, and HB are equal. Joyce, do you know what this means? Like, what is H on? Kimmy, do you know where H is on?
I don't know.
All right, we seem to be a bit stuck. But again, guys, remember, if H is equidistant from A and B, then H is on the perpendicular bisector of A and B, right? Does that make sense? Joyce, Lloyd, Kimmy?
Okay.
All right. Is that confusing? You guys are kind of silent. I don't know if you guys have questions or not.
Wait, that means if we. What do you mean? What does the H point mean?
Well, H, remember that we drew the perpendicular bisector of line AC right here and line BC right here. We drew these two perpendicular bisectors and H is the intersection point, right? And we just proved that H is also on the perpendicular bisector of AB, meaning that the three perpendicular bisectors meet at the same point H.
Oh, isn't that obvious?
Well,
We already
yes, it
have
can
one
be obvious, but
perpendicular line, but we have
as
another perpendicular line.
yeah, well, it is kind of obvious, but as mathematicians, we have to prove that it's obvious, right? All right, but does that proof make sense to you guys? Do you guys have any questions? Joyce, is this confusing? Lloyd, does this make sense to you? All right, well, I'm gonna, oh wait, okay, it makes sense, that's good. All right, so,
Kind of.
okay. What do you not understand? Like, tell me which part is kind of confusing.
Nothing's really confusing. I just don't get the point right here.
Oh, well, you see, we're actually building up to a construction because like you have to understand like what is a circumcircle, what is an incircle, because we're gonna do a really cool problem later that requires the knowledge of all this stuff. So just keep it in mind, okay? All right, so now we're going to talk about something a little bit different. We're going to talk about incircles. So let me delete all of this. So. All right, and to do this, we have to first start with the angle bisector. Okay, guys, I promise this seems a little bit boring right now. It sounds like a lecture, but we really need the knowledge of all of this stuff to do this really cool problem later. So hang on to me, all right, guys? Promise me? All right, so again, the angle bisector of an angle like CAB is the line segment that divides the angle into two equal angles, like this. You guys got that?
We're eyeballing it right now.
I know, but I'm just like telling you guys like what the concept of a angle bisector is. Does the concept make sense?
Okay.
Okay,
Makes
that's
sense.
good. All right. And now we're gonna prove something similar to the thing we proved with perpendicular bisectors. And we're gonna prove that if a point inside this angle right here is equidistant from the two line segments, then D is on the angle bisector of this angle. So we're trying to prove that if ED is equal to DF, then BD is the angle bisector of this angle right here. Does anyone want to help us prove it? So we know these are right angles, right? Because it's distance.
What this is not, the top one is not a right. Oh yeah, the top one is.
Well, since do you guys want to like guide everyone through how the proof is like? Do you guys know how to prove that the two triangles are congruent?
Yeah.
Kimmy, so how will we prove this?
Because even though we eyeball it, the lines are straight. And if you extend them, they they're straight against the other line. So that means they're right angles. Well, about right angles. They could be a few degrees higher.
Well, Kimmy, that's a very good intuitive explanation. But again, we have to be like really rigorous about how we prove this. So this proof, how we would do it is we're gonna use something called the HL congruence, which stands for hypotenuse leg congruence. And
So
how
that's
this
a leg.
well,
That looks more like a beak.
well, the leg is actually referring to the side in the right triangle. That's not the hypotenuse, which is ED right here. So that's the leg.
What is the hypothesis?
Oh, it's the hypotenuse. And it is the line, the side in the right triangle that's the longest. It's spelled like this, hypotenuse.
It's the line in the middle, right?
Yep. It's the line that is, you can think of it as,
What are the other lines? Are they just called lines?
well, it's called the side of the triangle, but in a right triangle, the longest side, the side opposite to the right angle is called the hypotenuse. The other two sides are called legs. So this is also a leg.
Okay.
Yep. But using this HL congruence theorem, we can conclude that these two triangles are equal to each other. which means these angles are equal. So D is on the angle bisector of ABC. Does that make sense to everyone?
Yes.
All right, guys, I promise we're really close to solving that problem. We just have to get through one more concept, okay? I promise, one more concept. Okay, so the final concept we need to know for this problem is we need to know that the angle bisectors of a triangle meet at the same point, which is something very similar to what we proved about the perpendicular bisectors. Remember?
Wait. Meet at the same point? That's not possible.
Wait, what was that?
That's not possible.
What is not possible?
Meeting at the same point. The 3 points on the triangle can't meet at the same point.
No, I'm
That's
saying like
impossible.
the 3 angle bisectors of the triangle.
Well, yes, duh, they can meet at the same point. So what's the catch?
The catch is that we're gonna prove that they meet at the same point.
Oh, that is a catch.
Yep, and we're gonna actually prove it like how we did with the perpendicular bisectors. We're gonna start by drawing 2 of the angle bisectors. So I'm gonna
Are
draw
they
these.
random? So
Well,
we're
you
just
can choose to
eyeballing
draw
them,
any
right?
2, but I'm just trying to draw these 2 because, you know, yeah, it's pretty random, but we're gonna start with 2 angle bisectors. Right? So these 2 angles are equal. And these 2 angles are equal.
Probably not.
Well, we'll see. And since we're actually going to use pretty much the exact logic from the perpendicular bisector proof.
Does that mean we just do?
What was that, Kimmy?
So, that's not working. So does that mean we just draw a line in the same place?
Kind of, Kimmy. Yep. Well, Kimmy, what did we just prove about angle bisectors? We proved that if it's angle bisector,
No,
then
I mean like, do we do? Cause like we know the point is like right here, F.
yep.
So do we just make a point right here along F that would hit the side? Let's say it's here. It's
Yep,
random.
that would be the 3rd angle bisector.
Yeah, well, what is the catch here? It's
Well,
the exact same as the old one.
No, Kimmy, not quite, because what we proved before was the intersection of perpendicular bisectors. Those are the lines like this, Kimmy.
So the point is different.
Yep, this is called the incenter. What we proved earlier was the circumcenter.
So this is the center of mass?
No, this is the center in which you would draw an incenter. Wait, actually, since
It's a center and in center. It's not a center.
Okay.
A center that's not a
Since
center.
everyone is kind of confused about why we're doing this, let me just show you guys real quick. All right. So a circumcircle of a triangle is a circle like this, right? Like it
Kinda.
circumscribes the triangle. It's around the triangle. Does that make sense?
Well, kinda, although it's magically uneven.
Well, the actual shape of the
Obviously
triangle doesn't matter. But the point
What
is,
do you mean by it doesn't matter? How
well,
does
you
that
see,
work?
we can draw any triangle. Like we can draw a triangle like this. Uh-oh. We can draw a triangle like this. And this circle right here would still be a circumcircle of this triangle because the circle goes through all of the vertices. Does that make
Why?
sense? Yeah, like
Okay.
look at the diagram. The circle goes through all of the vertices.
Okay.
Yeah. And
So
so point G is something called the circumcenter. And as we proved
Okay.
earlier, the circumcenter is the intersection of the perpendicular bisectors of the triangle. Sorry, that's not a very good line. It's the perpendicular bisectors, the triangle, meaning the lines that bisect a line segment and is also perpendicular to it. That's
this
what we
is not
proved
a
earlier.
good graph. This is not a good graph.
Well, Kimmy, would you like to draw a better one for us?
Well, one thing, it doesn't show anything.
What do
It's
you mean by
just
that?
like that circle, like this right here, this triangle has nothing to do with these three lines. They cross it, none of them align with here, or none of them go through the radius. So none of these lines are useful.
Well, you see, Kimmy, these lines are actually the perpendicular bisectors of the sides of this triangle right here. Of this triangle.
So the other triangle useless?
No, Timmy. The other triangle is also a triangle that can be inscribed in the circle.
Oh, so it means that one is not around the center, which means it's not actually like around the center. So it's not really going to be used in the graph.
Well, no, Kimmy, you're not getting the point here. What we're trying to say is we're telling you the definition of a circumcircle right now.
I know a circumcircle is like the center.
No, Kimmy, circumcenter is the center. Point G is the center of the circle that circumscribes this triangle right here.
A circumcircle is the circle.
That circumscribes this triangle. And also
Why is there so
circumscribes.
many circums?
Kimmy, there's only one circle.
No, I mean like why does everywhere like there's circles, circummeters, there's circumcenters, there's circumcircles, now there's whatever. I don't understand. What is like the point?
The point, Kimmy, again, we're building up to a problem, and this is a
What is the
concept.
problem?
Well, Kimmy, if you stop interrupting me, we can get through the quick lecture and we'll go on to the problem.
Fine.
All right. So, as I was saying, this is the circumcenter. It's the center of the circle that circumscribes the triangle, and the circle that circumscribes the triangle is called the circumcircle. And I was going to prove to you guys that the lines are concurrent, the angle bisectors are concurrent, but I feel like you guys are it's getting a bit boring, so we're gonna skip it. You guys can just accept that fact as true for now. And we're going to go on to the problem, but before that, I'm gonna define what an incircle is real quick. So
Now there's a not circle.
it's called an incircle.
Is that a circle inside of a triangle?
That is correct.
Okay.
An incircle is precisely a circle that is inscribed in a triangle. And the center point here, point A, is something called the incenter.
point A is the incenter.
Yep. It's called the
So give me
incenter.
it's guess. Let me guess. It's called the in triangle. The outside's
No.
called the in triangle.
No, not quite, not quite. But this is called the incircle.
And then outside's called the in triangle.
Oh, not quite, Kimmy. That's very creative, but not quite, not quite. All right, so now that we have all the concepts down, we're gonna do a problem that involves everything we just learned. So what we're gonna do is right now, if I give you a triangle ABC, I want you to construct the incircle for me.
The in circle, which means a circle is precisely inside the middle.
Yep, so I want you to construct a circle that is exactly in the middle of this triangle.
Well, that is kind of not possible.
Well, it kind of is, Kimmy.
Or we could just try a billion times. Well, we don't know how to make like a with Google's thing, with Zoom's thing, you don't know how to make an exact precise triangle.
Well, let's think about the objective here, shall we? What we're trying to do is we're trying to draw a circle that is precisely inside the triangle. Yes, Kimmy, something like what you just drew. And wouldn't it be really useful if we could find where the center of the circle is? Like, Kimmy, do you agree?
Oh, yeah. It would be very useful. Then we know where the center of the circle is. That way we would be able to draw the circle.
Yeah, so if we know the center, we can easily draw the circle. So let's find the center of the circle first. How do you guys suppose we could do that?
Let me see. Is it this? Is it this thing again?
Kimmy, you are very close. However, remember the intersection of the perpendicular bisectors. They intersect at the circumcircle, which means the one you
Oh.
just found will give us a circle like this.
Oh.
We want to find the center of a circle like this.
You just answered the question.
All right. Should I spill the beans?
Wait, let me think. Oh, I understand now, So if we start from B and do that, and then go to C and do the exact opposite. Well, go to B and do anywhere. A, right down the middle. That way we know the exact point.
Precisely. Okay, does everyone understand what Kimmy just said? So what Kimmy said is that since we're trying to find the incenter of the triangle, we know that it is the intersection point of the angle bisectors of the triangle. Therefore, if we can construct the angle bisectors of two of the angles, we could find the intersection point.
Which is
would be our
definitely not
circle.
that.
All right, does that make sense to everyone? Lloyd, Joyce, does that make sense?
Yes.
All right, Kimmy,
Yes.
I'm pretty sure. All right, that's good. All right, so I don't think Kimmy was here for that part, but Joyce and Lloyd, do you guys remember how we can bisect an angle using constructions?
Wait, is it? I think I'm actually seeing this. Is it this?
Yep, Kimmy, that's the line we're trying to draw, but like, how would you construct it,
Oh.
right? Well, since nobody remembers,
Oh wait, let me think. Is it like this? If we go straight down, this exactly intersecting. Well, that would be useless. And then Yeah, wouldn't it make sense? So that's
Can
the
we-
center point.
It does make sense. No, but the thing is, Kimmy, we're doing a construction problem, right? So everything you draw, including the line you draw, we have to construct it.
What do you mean? Like you use circles and construct a line?
Yeah, so I'm gonna go over
You can
this.
use circles?
Yes, Kimmy.
That's
It's part of
cheating.
no, it's part of the constructions, Kimmy.
I didn't realize we could use circles.
Okay, Kimmy, were you here when we talked about how to draw the
I wasn't-
perpendicular
I
bisector of a
wasn't
line?
here. I wasn't here for the first like 16 minutes.
No, but like last class though.
Yes.
Yeah, so do you remember how we drew?
Oh, I remember.
Yep, we can't use circles, Kimmy.
Oh. Now I remember. Well, I still don't understand.
All right, so we're gonna start off with a circle.
Do you mean like if we do 3 circles? Well, let me just ask a little question. This might be the solving point. If we do 3 circles here, wouldn't that center be this place where the center is? And then couldn't we do like a line down and then a line to the side? That would make the exact center.
Well, Kimmy, I think your idea is very creative, but we really just have to draw 2 lines.
What?
No, Kimmy, you already
This.
told. Yeah, we just have to
Yeah.
draw 2 lines right here. Yeah. And since Kimmy, I'm gonna show you right now how we can construct an angle bisector. So, Kimmy, would you agree that triangle DBE is isosceles?
Yes.
All right, so say that we construct the perpendicular bisector of line segment ED. Would you say that this line is the angle bisector of this angle right here?
Yes.
Good. So that's how we construct an angle bisector.
Oh my god. And then we just do it the exact same on the other side.
That is correct. Let me do that real quick.
Well, it doesn't matter how big the circle is, right?
It does not matter how big the circle is. That is correct.
Which means we can draw the circle that's boarding like very big and it would still give us the same answer, right?
That is correct, but it would get a bit messy.
I know.
All right. So, Kimmy,
So,
we just found the center of the circle.
but
Now what?
wow. Do this. Draw a
Well,
circle.
I know the natural instinct would be to draw the circle already, but the thing is,
Oh.
we don't know the exact radius of the circle, do we?
Oh, I remember now.
Right. So we're
I
gonna have
see
to
the
need
problem.
one more step.
A
We're gonna have
third
to
line on
yeah,
the
we have
top.
to we actually have to construct a perpendicular line from J to BC. So a line like this.
What?
Because we have to find an intersection point for us
I
to
get it,
draw
I get
our
it, I get
circle,
it.
right?
I get it.
Right.
So
And
that's it?
That's it.
Well, like, where do we know where is the exact radius?
What was that, Kimmy?
Which, like we could like, let's say, like, I just draw a line. I could have drawn it like this. I could have drawn it like this. And I could have drawn it like this. I could have drawn it like this. How do we know the exact radius?
Exactly, Kimmy. That's why we have to construct a perpendicular line, right?
Which means shouldn't we start from A, go to J, and then continue the line exactly forward?
Well, Kimmy, does the line that you drew look perpendicular?
Not really.
Exactly. That's why we have to construct a perpendicular line. That's really easy. We actually already went over this 2 weeks ago. Does anyone remember?
Wait a minute. Is it this? Is it? I'm just curious. Is it this? I draw a circle in the middle. Another circle here that's going to J, like right here, and another circle right there. That way we can feel the exact center.
Kimmy, I think you got it. Well, what we do is we start with a circle that kind of overlaps this line segment here a bit, right?
Hmm.
So you
Or
draw
we
a
could
circle
go
that's-
to F and J.
right, and then we would draw the other intersection point. And then we just use the same old tactic that we always use. We draw two circles, we get their intersection point.
Oh god, now it's messy.
I know. I could hide the objects if you want, but I think this looks pretty like creative and cool. So, but if it's
And
too messy, I'll hide the
distracting.
objects. Do you guys want me to hide the objects?
Could you hide the outside circles? Because I don't think we really need the outside circles.
Of course. Okay, let me backtrack a bit so I know which ones to. Okay, so we're hiding this one.
How do you?
I don't think it's working. Oh, here it is.
Oh, it actually looks way better now.
Okay, it is not allowing me to hide this circle for some reason.
I understand now. It's because you drew two circles there. You're hiding one, and then you're revealing one, and you're not hiding the
Oh.
other one.
That makes sense.
Oh no.
It's fine. I'll just hide the other ones. It's much clearer anyways. Is that fun with you guys?
Yeah.
All right. Okay. And
Oh,
I'm gonna
that looks way
resume
more clear.
our progress. Yeah, in fact, let me hide this line too. We don't need this.
Need these two lines.
All right. So as I was saying, we just resume our
Now
progress
it just
here.
looks like we made some of the most exact lines possible.
I know that is indeed the entire point of constructions. So we finally have this exact point, and to finish the problem off, we draw the circle. Pretty cool, huh?
Well, what does it look like if you unshow everything?
That's
Like,
what I'm gonna do right now.
that one just don't matter. Oh my god, that. Wait.
It's a pretty precise circle, isn't it?
Yeah, and then show everything. I want to see what happens when you show everything.
That's what it looks like.
Oh my god, it looks so messy.
I know. Well, if you actually construct this on paper, it's like you can only draw parts of a circle. You don't have to draw the whole thing, which makes it a whole lot easier.
Oh yeah, you only have to draw the part of the circle that you need.
Yeah, but unfortunately on the computer, we have to draw the whole thing. Okay, so does this make sense to everyone? Because I have another problem I want to do real quick. It's really cool.
Yes.
All
Can
right.
you erase? Oh, never mind.
What was that?
I wanted you to just prove that is exactly in the center.
All right, sure.
How do you like exactly prove that it's exactly in the center?
Well, Kemi, if you want an intuitive understanding, you can see that when we drew the circle, these points were exactly on the line, meaning these segments are all equal. So it's exactly the same distance from every side of the triangle.
Ah, I get it now.
Yeah, so that's an intuitive explanation. So I'm gonna
I get it now.
yeah, I'm gonna go ahead and show you guys the other problem right now. I want to delete everything. I'm just doing this to
That
hide
makes so much sense now.
that's good. All right, so what we're gonna do right now is I'm gonna give you a circle. And I'm gonna pretend that you never saw the center. And I want you to construct the center of the circle for me. By the way, Kimmy, I like your background.
It was just random to block off the back.
All right, but anyways, like again, we want to construct the center of the circle. Like we don't know where the center of it is. So how will we construct it?
How did you draw a line? How did you draw it?
Draw the circle?
Yeah.
Well, I actually drew the same circle and I just hit the objects.
Now we know where it is.
Yeah, but like the point of the problem is to think that you don't know where it is and we want to construct it.
And you can't really exactly pinpoint that point. Because what I think right now it is on is that, like, I think it's about right here.
Yeah,
Where's
but
the actual point?
what if you're off by like 0.0001 centimeters?
No, but where's the actual point?
Like, you want me to show it to you?
Yeah.
Right here.
Oh my god, I missed it just by a tiny bit.
I know, Kimmy, that's why we're gonna construct it.
But that was very close. And that was
very close
lucky
indeed.
shot.
All right, so Kim, guys, how do you think we could construct the center of the circle? I'm gonna give you guys a hint and I'm gonna draw this triangle right here.
Oh, should we just draw a triangle and figure out the triangle and then we'll figure out the enter? So, random idea.
Kimmy, that was a good random idea. Keep on going.
Random idea. Circle here. And then circle there. And then the point's right here. And then make another circle right here on the point. And then make it right back like this. And we have two circles.
So are you trying to construct a perpendicular bisector or an angle bisector?
A perpendicular bisector. No, I mean like an angle bisector.
Well,
That way we can make like the diagonal line. I can't draw a diagonal line with the circle.
But if you draw the angle bisectors, you do realize you're constructing a circle that's inside the triangle, right?
Oh. Okay, I get it. So we're finding the center. Oh, so we're finding the center of the circle.
We would want to construct a circle that's outside of the triangle, right?
Oh, that means we should make it like a perpendicular. Like it's supposed to be like.
That is correct,
kind of like
Kimmy.
this.
Yes, this is a very
around
simple
it.
problem. That is correct,
But
Kimmy.
how do we do it?
Whoa,
That's
Kimmy,
the
that actually goes back to 2 weeks ago, doesn't it?
Oh, I get it now.
So,
I think I might get it.
do you want me to go ahead and draw it, or do you want to draw it?
I'll try.
All right.
I know we need to find. I think we just draw a circle anywhere.
No, not
No,
quite.
not there. Like right here. We draw a circle here. So what I'm trying to find is like the like diagonal line right here. That way we can make another line right here
That is correct.
and then do it. So right now I think what we should do is draw a circle right here.
How big?
2D, point D.
Okay.
Make another circle from point D all the way back to point E.
All right.
And then now we can make the exact line. And then now to pinpoint the other places, right now we need to draw a circle on on D, on D, 2, O. No, actually, never mind. To the line. The
Which
line. Oh, like anywhere on this line, I think.
Okay.
Yeah. Oh, actually, make it like right here, on the point right there.
All right.
Make another one right here. Also going to the same point. No. From E.
Okay.
To the point H. Now we can. No, I just made a tinier circle instead of a circle.
Timmy, the first circle is good, but are you sure you want to draw the second circle at E instead of C?
Oh, I get it. Put the C to the H, I think. No.
Well, Kimmy, there's a tiny problem. What if you do this instead?
Oh, it's a tiny bit bigger.
Yeah.
It's just a tiny bit bigger.
And what if we connect them?
Oh, it makes the diagonal pinpointed right there.
Exactly.
It's pinpointed right there.
All right, Kimmy, I'm gonna need you to delete the annotations real quick because I'm about to do something really cool. So I'm gonna
Can
draw
you
a circle.
pinpoint it even more? Oh my god, that is the exact size.
Yeah, you see what we did there? Wait, okay, this is kind of hard. So I'm gonna draw a circle centered at J. If I draw it to here, it makes the exact
Oh my god. Can we
same
actually like show the point?
circle.
I wanna see if it's like it overlaps and it breaks.
Yep, it's exactly there.
You can't even see the point because you broke it.
I know,
so
because
broken, you can't
it's
even
literally
see
the
point.
same place.
That's amazing.
I know, right? It's pretty cool.
And hide everything except for that point. That'll look so cool. Except for that circle and that point and that triangle. I feel like that'll be cool to watch. Oh my god, find the exact center of a circle.
Yeah, and you can keep drawing circles that go to the exact same place.
Which means they'll keep on going to the exact same place unless you change the places.
Yep, that is correct. All right.
Okay, good one.
Are
It's
there
like
any
9
questions?
circles overlapping each other.
What was that?
It's just 9 circles overlapping each other.
I know, right? You can draw infinitely many of them.
Unless you get your thing 0.0001% off and you spoil everything.
And like, in fact, like the circle is becoming so dark because there's so many circles over it.
Oh my god, it's actually becoming so dark. And I feel like the computer is getting a little laggy.
I know I should stop doing this. All right, but anyways, are there any questions on what we just did? Lloyd, Joyce, do you guys have any questions?
Well, like, how do you draw this circle if you actually don't?
What was that, Kimmy?
Like zoom, it doesn't actually, if you pinpoint the center, you draw it like this. So how do you actually know how to draw the exact circle on zoom?
On Zoom. Oh, you mean like using the annotations?
Yeah, because it's not possible to do that. Because like when you click on it, it's not actually the center. It's the starting point.
Oh yeah, Zoom is pretty weird. So, I mean, I don't really use this that much, so you're gonna have to figure that out on your own, Kimmy. Yep, it's
You
pretty
see?
weird.
Which one?
Oh, shit.
But that's all we have for today. So if you don't have any questions, thank you for attending Inland Empire Math Circle. Bye.
Is there more?
Not quite, Kimmy. Not really, but maybe next class.
Okay,
But
bye.
thank you, everyone. Bye. Good job, Kimmy. You did great.